Speaker is Samoilenka, who will tell us about the microscopic theory for electron quadrupling condensates.
So it just appears on archive, so here if you want. I'll start, it will be roughly two parts. So one is more general theory for this kind of condensates, but then the second part is more specific solution for the theoretical quadrupling. So I'll try to go through first part probably faster. Work?
No, it doesn't.
Okay, sure. First question, just to set up the stage. So what is the order parameter for quadrupling, which we saw for counterflow quadrupling? This would be some linear combination of this type of operators, and I'll draw by F operators corresponding to fermions and by B to bosons, and then this X, Y, Z, and so on is combined index of all the spin, band, time, and so on. The first problem is that this order parameter is fourth order in fermionic operator, so it's hard to do some kind of Mill field. So first step is kind of introduce auxiliary fields. In this case, this is like bosonic fields, which would correspond to like pairs of fermions, right? And yeah, similarly here. So in that case, I will start for the generic kind of derivation from this kind of action. So there is a kinetic term, there is an interaction term, which is quadratic in fermionic operators, and then there are these two parts, which is the small v will be responsible for superconductivity, and this one will be like a repulsive interaction in general. So you can imagine that if you diagonalize these interactions in terms of pairs of electrons, this will have negative eigenvalues, this one will have positive eigenvalues. Right, so to introduce this auxiliary bosonic field and to like reduce the order of the interaction in the fermionic fields, I do have a Stratonic transformation. So this keeps the model exact, but introduces these B's. And I do it only for the small v part, for the superconducting part. Now my B would basically correspond to pairs of fermions, right? And then I introduce min fields, and I do it in the following way. So I add and subtract some terms to the action. And so this is the part that was the underlined with the red line is the initial part, the kinetic part for bosons and fermions. And then the others were added. So all of the others are min fields, so this C, P, D, and so on. I also subtract them, and then it will be in the next part, in the next slide. And so here, all the min fields can be responsible for different things. So for example, this one just renormalizes the fermionic Green's function, so it could be like fermionic disease or something. If it breaks corresponding symmetry, of course. So this delta is the usual superconducting order parameter. This D is also responsible for superconductivity, but it's kind of like rudimentary and it could be removed. So this P would correspond to charge E quadrupling, and this C again normalizes the propagator for the bosons, so for electron pairs or fermion pairs. And so if it breaks corresponding symmetry, it will correspond to counterflow quadrupling. So in this sense, see that its prefactor is kind of quadratic in bosonic field, so, and for this one, charge E also. So in a sense, it effectively is quartic in fermionic fields. Right, so in total, I don't change my action, so my action stays the same. So I have this S0 part, which is at most quadratic in the operators or fields, fermionic and bosonic, and then I say that I have some auxiliary field or like auxiliary number xi that I will expand in, and I say that for xi equals to 1, this action should be the physical one, the initial one. But then if it's 0, it basically removes this delta S, and it's solvable. So that's why you can expand in powers of xi and get some diagrammaticity. So this is the delta S. So it's actually there is much freedom in how you what would be how these prefactors will be functions of this size in general, and for this case, it's just one of the simplest choices is just I multiply by size here, and all of the mean fields, which are the other part which was subtracted, they are like expansions and some orders of psi. So this is basically like this shifted action or in general, or homotopic action formalisms. That works for like diagrammatic Monte Carlo. And then how do I find mean fields from that? And yeah, by the way, I think maybe some people call this, or maybe all the people call this like quantity terms. But probably I'll stick with calling them all mean fields. And how do I find what is the solution, like what mean fields, what this mean fields should be equal to? And so the answer is this basically variational perturbational theory, which is also was mentioned before a bit. So the point is that if I construct my grand canonical potential, I obtain self-consistency equations as derivatives with respect to all the mean fields. So basically, yeah, that's the criterion how to find the mean fields, and more kind of, let's say, a bit physical approach is that we will search for mean fields to be minimum of them, but in general, it's just extreme. So another simplification that I will not discuss how I obtain, but the point is that it's harder to do it just in initial canonical potential and so on, but I can basically use like this skeleton version of it, so I can remove all the sub-energy insertions and so on, and this simplifies greatly like the equations, and also the mean fields now, always CP and so on, they are sums over all these orders and psi, so it's in this sense it doesn't matter which way they separate in the orders. Right, and so this basically produces the self-consistency equation. So either derivative of this with respect to all the propagators, or derivative of this skeleton canonical potential with respect to mean fields. And this type of thing is related to like this Baum-Kadanov and Tutinger-Ward, if I'm not mistaken, formalisms. Right. So now I will go to some more specific example for the PTRS quadrupling. In this case, I will be looking only at quadrupling and normal state properties. So basically, I set all the other mean fields to 0. Now I will just have only this C mean field, or like the one that corresponds to quadrupling, and just to write it down. So basically, I will denote the propagator for the boson. So for over pairs, basically is R, and it's a red arrow, and Green's function, free particle Green's function for fermions, or for electrons in this case is this black line. So I expand my grand canonical potential, like it's in skeleton version. So no, and then I obtain the following form, and yeah, some zero order terms. The point is that, so for example, this bubble with only one bosonic propagator corresponds to the simplest BCS model. If I would remove all the other ones, then it will produce the usual TC and so on, and just superconductivity. So in this model, by the way, since I study quadrupling on normal state, so I can see the normal state, the quadrupling state, and the point where it transitions to superconductivity, but I cannot go into the superconductivity because I set delta to 0 basically. Right, and in this model I added a lot of the terms, so I expanded up to like 6 order in that psi that I showed before. So I don't show all of them, I just show some of them. So for example, these ones would be some of the like so-called fluctuation corrections to various quantities, and then these diagrams, this type of diagrams, I believe the ones that allow for the quadrupling to appear. And basically the logic here, yeah, I will not like go it more rigorously, but just to know the intuition. The point is that now this bosonic line, it connects, it can connect the two fermionic lines in different bands. And this turns out to be the important part, because like this here, for example, it will connect the fermionic lines in the same band in the it will be basically symmetric in this sense, right? And so this is the specific model that I studied. So in this case, this is the kinetic part. So this is basically the fermionic models of electronics. So I have three symmetric electronic bands, so labeled by this alpha, right? So it's the same kinetic part for them, and so this is the interaction. The first part is again responsible for kind of like superconductivity, right? So this matrix is defined like so, and it has three eigenvalues minus lambda, and 0. So basically, lambda is positive, so these are negative eigenvalues. So this is attractive interaction. Then this is just a density interaction, and it's repulsive, so it's positive. Right, and so just to remind you, probably saw this picture before today. So in this work, I basically study some kind of simplest possible model that might describe somewhere along this line. So at the basically tip of this, so it starts from superconducting DC and goes up. So I can describe normal state and Z2 voltage state. Right. I wanted to discuss also some like freedom in how these bosonic fields can be parameterized. So basically, the point is that you can always do something like this, transformation like so with unitary big B, and just to remind you, this R is a propagator for these bosons, or right, and so these bosons are Cooper pairs in a sense, right? And then there are like infinitely many choices, but like some popular ones that so the one on the left will be basically that Igor and Julian likes, I suppose, and the one on the right is more closer to the one that Sankit used, for example, in one of the previous talks, right? So the point is that first choice, you can just put all the you diagonalize your eigenvectors to choose them real, and the second options, you basically diagonalize your bosonic fields in S plus minus AS basis in this case, and it means that your propagator R11 would correspond, for example, to R S plus AS state, to S plus S state, and to 2 will correspond to S minus AS state. Right, and then, for example, this is how the time reversal transformation would work in this kind of models, ignoring all the like superconducting fermionic degrees of freedom. Just Julian, for example, was talking about like superconducting. So this is just for this BTRS ones, and for them in this representation, it would just correspond to complex conjugating any scalars, where B and F fields are not scalars, right? And for these diagonal representations against complex conjugations of scalars and swapping of the bosonic components. Right, and then system is time reversal symmetric if in this interpretation this propagator R12 is real. And you can also imagine that if you put like same position space and so on, this criterion basically says that B1, B2 star is real. So imaginary part of that is 0. So this is like equivalent of, for example, Julian was saying that like, or the interpretation of that phase difference in this case is 0 pi between kind of like different bosonic components. In this in the other representation is in S plus minus S basis. It means that basically these propagators are the same, or in simpler terms, maybe that the number of plus and minus components is the same. So in this case, the time reversal symmetry is not broken if you have the same number of S plus AS and S minus AS Cooper pairs. Right, and then on the other hand, the time reversal symmetry is broken if this R12 is imaginary, so there is some phase difference which is not 0 or pi. And in this representation, it means that there is different number of S plus S and S minus S Cooper pairs. And so the point is that I think this is like then the simplest interpretation of what's going on, because you can say that this BTRS can be broken in superconducting state, of course, because you can have a situation where you spontaneously have more of S plus S or S minus S pairs, but then this could also happen in not superconducting state, and this basically means that number of preformed Cooper pairs like S plus S and S minus S pairs spontaneously becomes not equal, and this is the BTRS quadrupling state. Right, and this is just to at the bottom. I wanted just to highlight one moment that I think many people kind of brush over, that there is actually like a difference between fermionic bands and bosonic components, or like superconducting components. So for example, here is psi1, psi2 are the superconducting components, but they are composed as like they are represented by a linear combination of from the fermionic bands. So this 1, 1 and the 2 here, for example, are fermionic bands, and they look differently. So, and yeah, this is like specific representations for this one and this one, how they look like. Okay. And let's continue. So yeah, I studied this model in V coupling limit, and here basically the point that basically in the limit where this is true, so I assume that the chemical potential is much bigger than omega d by and is much bigger than TBCS, which is just the usual BCS critical temperature that sets some order, and this omega f, yeah, I don't know how to denote it, but the point is that this is like a cutoff scale for the bosonic frequencies and momenta. So this Vn is bosonic Matsubara frequency, Vf is Fermi velocity, and Q is momenta for this boson. So it's basically momenta of pairs, electron pairs. Right, and then yeah, I will also use this notation, this FHS, W, and so on. This is like just some dimensionless parameters which are assumed to be small, smallish, kind of. Right, and this, yeah, so the model will look like something like that. So in this approximation, I assume that, yeah, this, eventually I will assume that this will be just, yeah, one more point. This is static approximation. So, for example, since I assume that, yeah, this omega n is quite small, so Vn is small. So basically, I take into account only like zero, n equal to 0 part. So it's the static approximation for this, but and yeah, of course the Q, so momenta for Cooper pairs is there is some cutoff, so which is basically given by this omega f, right? So I obtain the following form. So it's the first parts, and then this D1, D2, D3 are some like different diagrams which are power in the first and second and third power in terms of this R. So in terms of pair propagator. Then so yeah, basically this is the form that I use it for. So the point is that I can take the first order in R terms and absorb them into the definition of C, and they will give me this Q dependence, and they will change this also term. But yeah, so the point is that I remove the first order ones, I absorb them, and then I obtain the following form, assuming that the remaining part of this C is momentum independent. So like the simplest approximation. Right? And so in general, it should be like this R should be like 2x2 matrix, right? Because I have now two bosonic components, but basically show that, well, not here, but like in paper, I showed that it's the energy is minimized when this R is diagonal, and so basically off-diagonal terms for this, for example, epsilon AB or for this RAB are they can be removed. So the minimum is obtained for them to when they are 0. And so I will just use the following notation. So I'll have only the diagonal parts, which are this the one corresponding to S plus S and to S minus S. And yeah, just to remind you, this basically if it's yeah, maybe I'll just show it. Yeah, basically right here. So then I can introduce the foreign variable. So this is for 2D system now, some solutions. So if I integrate over momenta of this propagator, bosonic propagator, I obtain the following form. But the point is that I rescale it somehow. So this L plus minus will be rescaled these propagators, but probably the simplest way to say it is that this L plus minus is a rescaled number of bosonic particles in the plus or minus component. Or in other words, this is rescaled number of Cooper pairs, or like S plus S and S minus S Cooper pairs. Right, and obtain the following form of the energy, energy functional, or grand canonical potential, again rescaled, and then 0 other part and so on, but I'll maybe point out some main points is that, for example, this is part quadratic in L's, again quadratic and then cubic. Then first point is that these lambdas are positive generally, and if I would include, oh yeah, and this L minus, it's proportional to strength of the density-density interaction squared. So if there will be no density-density interaction, like additional repulsion, this would be 0. And if I wouldn't take into account the third term, actually in this model there would be no superconducting transition, just because it will be just positively defined always. And in this case, I can say that, for example, normal state corresponds to a configuration where, again, number of plus and minus pairs are equal, so L plus equals to L minus, but then BTRS state would correspond for them to be not equal, and the superconducting state corresponds to case when they diverge, or they just basically diverge, they become very big. And in this case, like since this 2D system, it's also a bit weird situation, because in principle this model is since this is third order, it always diverges to minus infinity for L plus minus going to infinity. So, but there are cases where there are local minima, and so in this case, the normal state is interpreted as a situation when there is a single local minima, or BTRS if it's 2 local minima, and superconducting when there is no local minima. And yeah, and this term basically is responsible for the case where it becomes favorable for this one minimal to split in 2. Right? And yeah, this is basically repeating what I said, that normal state is they are equal, and not infinite BTS quadrupling they are not equal, and superconductivity they diverges. Right, so this is some of the solutions. So, for example, on the first plot, this is this L plus minus as function of temperature. It's normalized over TBCS, so like TCS critical temperature, which like, is just a scale in this case. So, for example, if it's roughly 1, you see that the L's increase. So this is basically saying that when you temperature becomes lower than BCS critical temperature, you so in this sense, this TBCS is roughly T star. So it's like a temperature when Cooper pairs start to perform. So this is the point that L's increase. It means that you have more and more number of Cooper pairs. And so, for example, this is for different values of density-density interaction. So if you pick, for example, 0.4, you see that at some point it splits, so this green line, and when it splits, it basically spontaneously breaks this BTRS symmetry, and like L plus, for example, is bigger than L minus on the opposite, and yeah, this is the BTRS state now. Then if temperature becomes even lower, then diverges, and the system goes to superconducting state, like left of this plot. This is plot a similar thing, but maybe in different coordinates. So this is temperature again on vertical axis now. This is density-density interaction, and then we have some regions. So this is normal, BTRS, and superconductivity, BTRS superconductivity basically. And the point here is that when density-density interaction becomes too small, the BTRS quadrupling state disappears. Yeah, one of the features of this 2D system, of course it should be like BKT and so on, but in this case, the fluctuations that they take into account just basically change the critical temperature of superconductivity to some specific value of like 0.78 times TBCS. So it's somewhat lowers it, and it stays like that for roughly, right? And yeah, we can also estimate what is the minimal value of this lambda minus or density-density interaction when the BTRS quadrupling is present, and it is in the deeply weak coupling limit. It's exponentially small. So in principle, in the weak coupling limit, all of this almost certainly all of this space between this superconductivity and T star would be a BTRS state. Right, so this is the 3D model. Again, the same thing. I just compute the number of basically this L plus minus variables, which is again a rescaled number of Cooper pairs in plus and minus components. And in this case, it's not. It's bound to this region from 0 to 1 in 3D case, and so this is the model, which looks quite similar. There are some changes to this term, but it doesn't matter that much. The point again, I have this term lambda minus, lambda 3, and so on. So it works similarly, but in this case, it's always, in a sense, bounded from below. We are only in this region from 0 to 1 for L, and so in this case, actually, all the states are like normal if the global minima is only singular and symmetric, and then BTRS quadrupling if there are two global minima which break the symmetry, and then superconducting when there is no minima, and effectively L plus or minus or both go to 1. Right, so, basically this is what I said. Right, and these are some of the solutions. In this case, it's the range of temperatures where I see this quadrupling state is extremely small. So this is for quite somewhat away from this weak coupling limit, and in this case, this is like a very, very small difference, but in principle, it is still there. So I still see that as I decrease temperature, my number of performed Cooper pairs increase, and at some point it splits, and so this is the BTRS state here, and the normal to the right, and superconducting to the left of this point where it intersects with the one line. When it intersects, the system goes to superconducting state to the left. Right, but in this case, we of course observe that this superconducting transition temperature, it's very close to TBCS estimate. So, and in the deeply weak coupling limit, in a sense, it's exponentially close to TBCS, which is, I suppose, is expected. Right. So I calculated also some other things as observables, like specific heat in this case, just derivative of canonical potential, and for 2D system on the left and for 3D on the right. And they are rescaled somewhat as function of temperature. And for example, in 2D, you see that the first So yeah, this is specific heat due to only like flare propagator and so on. And so as I lower the temperature around the T star basically, or TBCS in this case, are roughly equal, I see the increase. This is basically Cooper pairs being performed. Then there is kind of this step, and then this last increase is transition to superconducting state to the left of this. But then if you zoom in somewhere here, it's invisible here, but this is the zoom in. So there is actually a very, very small jump at T-BTRS. So at the transition from normal to the right and BTRS to the left state. In 3D, it's somewhat similar, that it's like performed Cooper pairs increase the specific heat, and then at the BTRS there is a jump, although the height is bigger in this case, but the regime of temperatures is very, very narrow, so that's why it looks like that. Right, so I also estimated how the density of states, like electronic density of states due to this propagator look like, and I just took this formula, and the point here is that this is only only like first order estimate, so only this diagram is included when calculating this Green's function. So for example, this again 2D, 3D systems, and this plot should be like symmetric for negative energy, so the x-axis is like energies are scaled, and the y-axis is change in density of states. And in this case, for example, for this is comparing BTRS state and normal state, which would be at the same point basically. And here the point is that for BTRS, this deep in the density of states is lower, but it's also somewhat narrower. Right, and so yeah, this is probably the last point, that I also computed how the value of basically this lowest point at Fermi level effect basically depends on temperature. So in this case, this is again 2D, 3D, and as function of temperature now. And so this is, for example, with minus this change. So first you see that it there is this change increases again due to performed Cooper pairs, and then there is this like a kink change in derivative at the TBTRS, and similar in 3D. And so yeah, this could be something that might be observable. And I mean, the point here is that why it happens is that when like this change in density of states is just a sum of the density of states for S plus S and S minus S components, and when it's normal, they are equal. But if it becomes BTRS quadrupling, they become non-equal, and it's dominated by like the biggest one of them. And as you saw, for example, on these plots, right, like the rate of change of this number of particles in each component changes abruptly at this point. So it's like this causes that kink on the density of states. Yes, and that's it. Thank you.